So we've talked about in previous videos how if you have a cubic function, when we did the derivative, it ended up as a quadratic function, as noted in the bottom example here. The two middle examples, notice we start with quadratic functions. They end up as linear functions for the derivatives. And if we have a linear function, it ends up as a constant. Now, one thing we also saw, but it's not up here, if we had a constant, the derivative we saw was 0, because if it was like y equals, say, 5, the slope there was always 0. So the derivative would then be 0. So, derivatives of polynomial functions, there is a pattern that we don't have to use the definition of a derivative every time. Notice we have 3x plus 1, derivative was 3. 3x squared plus 2x, derivative was 6x plus 2. X squared plus x, we had 2x plus 1. Negative 1/4 x cubed minus 2 became negative 3/4 x squared. Can you find the pattern? Well, to start out, we said if we have a constant, where c represents a constant, the derivative of that is always 0. The reason being, our slope of a constant function, like y equals 5, is always 0. If we have the function y equals x, the derivative of that, now remember d over dx is just one of our ways of representing the derivative. This is saying the derivative of the function x is just 1. Because if you have y equals x, your slope is always 1. Similar to back here, when we had y equals, or f of x equals 3x plus 1, the slope is always 3. That's why the derivative was just 3. So if we had x squared, notice here in this third one, we had x squared plus x. Well, the x squared part eventually turns into 2x. So the derivative of x squared becomes 2x. Where that's coming from is the 2 multiplies what's out front, which is just a 1, and then your exponent is going down 1. So really, this is 2 to the first. If we have x cubed, the 3 will multiply the 1 out front to give us 3x. And we know a cubic should then become a quadratic, so it goes down 1, so 3x squared. If you have x to the fourth, the 4 multiplies the 1 out front, so 4 times 1 is 4, x. And if you add a function to the fourth, the derivative should now be to the third. So in general, if you have x to the n and want the derivative, the n should multiply the 1 that's out front, so we'll have n times x, and our exponent needs to go down 1. So we'll now be raised to the n minus 1. And that's for any polynomial that you might be taking the derivative of. So if you had x to the 6th, the 6 multiplies with the 1 out front, and we'll now have x to the 5th. If you had x to the 1,000, the 1,000 multiplies the 1 that is really in front of the x, and you get 1,000 x to the 999. Likewise, we have 4t to the third, and we'll have 3r to the second. Now notice in doing these, we have some different notations for the derivative. We have the f prime of x in the first one, which is really common, and the y prime. Because t is our independent variable in the third one, we're dy dt instead of dy dx. And we saw back here, d dx, the derivative with respect to x is how that would be thought of. Well, this is now in the fourth one, the derivative with respect to r. That's why it's 3r squared. Okay, what about things that aren't nice, like the last few? If possible, always try and write it as something raised to a power. this is the same as saying the derivative d dx of x to the negative 1. Because this is really x to the first, so to bring it back to the numerator, it just becomes a negative exponent. So following the same rule, the negative 1 will multiply the 1 out front, so we'll have negative 1x, and it's now raised to the negative second, because it's got to go down one more. Now you can leave it like this, or if you want, if you like to have positive exponents, you can move that x to the negative 2 back to the bottom, and we'll have negative 1 over x squared. So when you switch where something is in the fraction, remember the sign of the exponent just changes. Okay, what if the exponent's a fraction? Well, it's the same idea. Let's write it as d dx of x to the 1/2. Okay, square root is the same as raising to the 1/2. Cubed root is 1/3. Remember, just like trees have roots in the bottom, fractional exponents, the root is in the bottom. So whatever your denominator is, that's the part that's the root. And we'll follow the same procedure. The 1/2 multiplies the 1 out front. We'll have x, and this is now raised to the negative 1/2. And where that is coming from is if you take our exponent that's currently a half and subtract 1, you get negative 1/2. So again, you could leave it like this, or this negative 1/2 can move to the bottom of the fraction. So you could write it as 1 over 2 times x to the 1/2. Or that could also be written as 1 over 2 square root of x. So if the question asked for to do the derivative, any of these would be correct answers. So a few practice ones. Let's rewrite f of x in terms of something raised to a power. This would be x to the negative 2. So to find f prime of x now, the negative 2 will multiply the 1 out front, and we'll have x to the negative 3. You can leave it right like this. That's probably the easiest thing to do. Or if you want, you can move the x back to the denominator and make it negative 2 over x cubed. In letter B, we'll again write it as x raised to a power. Remember, roots are always on the bottom of the tree. Roots are going to be the bottom of our exponent. So we'll be raised to the 2 over 3, the power of 2 and the root of 3. So y prime, the 2/3 will multiply the 1 out front times x, and our exponent has to go down 1. So 2/3, when you take away 1, that's like saying 2/3 minus 3/3, which will give you negative 1/3. So again, you can leave it right like this, or if you'd like, an equivalent answer would be 2 over 3 x to the 1/3, because moving it to the bottom makes it a positive exponent. Or you could also write this as y prime would be equal to 2 over 3 times the cubed root of x. Any of these would be correct answers, because they are all equivalent. Now, the easiest thing might be just to leave it as 2/3 x to the negative 1/3. It's a little less work. So basically, this makes our lives a lot easier when we're dealing with polynomial functions. We can take the derivative now without having to use the definition of a derivative. From this point forward, we will use these rules unless the problem specifically states, using the definition of a derivative, find the derivative. And then we'll have to do our h approaches 0 or our x approaches a way. If it doesn't state that, we can now use this power rule to find our derivative. We can also use it to find, say, tangent lines, which we've seen before, and something new is what's called a normal line. So the normal line to some curve or some graph C is through the point and is perpendicular to the tangent line. So basically, we can find the slope of the tangent line by taking our derivative and plugging in our x value, and then just use the perpendicular slope. We can flip and negate it. Okay, and the normal line is used in the study of optics with the rays of light. So we're going to try this example, find both the equation of the normal line and the equation of the tangent line. So first, remember it might not always be given to you nice. We're going to rewrite this as x times x to the 1/2. Because currently how it's given it to us, we don't have a derivative rule for that. X times x to the 1/2, well, when you multiply, you add your exponents. So this is really y equals x to the 1/2, which for us, it'll be easiest to write as to the 3/2. Now this is something we can just use our regular power rule for derivatives. Y prime will equal, we'll bring the 3/2 out front, x to the 1/2. And sometimes it might be easier to think of this as this is 3/2 really times square root of x. Well, we know we're working with the 0.11. For our tangent line, we can plug in 1 and get that our slope will be 3/2 times the square root of 1, which is just 3/2. So we will work with 3/2 for our tangent line. So we'll have y minus our y value of 1 equals the slope of our tangent line times x minus our x value, which was 1. Now, the only thing that's different for the normal line is that we need to have the perpendicular slope. It's still passing through the same point. So in this case, we'll have y minus 1 equals, and if you remember back to geometry, perpendicular slopes, you flip and negate the slope. So we'll have a slope of negative 2/3 times x minus 1. Now for each of these, if you wanted to, you could get y by itself. The only reason you would really want to get y by itself is if you had to graph it, okay, so that you could put it in your calculator. And you could even just add the 1 over and leave the rest even without distributing it and put it in your calculator that way. When you put it in your calculator, the blue here is our curve. The red is our tangent line, the one with the positive slope there. And then the normal line is the goldish yellow one that is perpendicular to it. So we're going to go through some derivative rules. What this one is saying is if you have a constant times some function, so say like 7 times x cubed, let's say. This is saying you can keep the 7 out front and just do the derivative rule for the function. So this would be saying like do 7, take the derivative rule here, which we know is 3x squared, and then just bring the 7 back in. So it's really just 21x squared. So that is what's really happening. The quicker way to do it is, as I mentioned on the other slides, it's like we're multiplying the exponent by the 1 that was out front normally. Well, now just think of it as it's a 7 out front. So the quicker way would be to say, okay, we're doing 3 times 7 to give us 21, and now x's exponent has to go down 1. So that's the quicker way. What's really happening is you're ignoring that constant, doing your derivative rule for the function of x, and then multiplying the constant back in. If you have two different functions that are both differentiable, you can take their derivatives separately. So an example of that would be, say we had 3x squared plus x cubed. Individually, they are both differentiable. So this is saying we can just take their derivatives separately. So 3x squared, 2 times 3 gives us 6, and we'll now have x to the first. And x cubed would be 3x squared. 3 multiplies the 1 out front, and then we have x to the second. So if things are being added up separately, we can just take their derivatives individually. Same thing is true for subtraction. Okay, similar idea, just a minus. Now notice we did not say it's true for multiplication and division. Okay, we will see eventually how we have to approach it when it's multiplication and division. For right now, it's only when it's addition and subtraction. So, if we have 3x to the fourth, the 4 multiplies the 3 out front to give us 12. Then we'll have x now raised to the third, because the power should go down 1 each time when you take a derivative. If we have negative x, well, this power is 1, so negative 1 when we multiply out front, and we'll really have x to the 0, but x to the 0 is just 1. So it's actually just a constant of negative 1. And if you think about it, y equals negative x is a line with a slope of negative 1. So no matter where you look on that line, the slope will always be negative 1. So it makes sense that your derivative is a constant. Now, putting together our addition and subtraction rules for this long string of polynomial, with our definition of a derivative, this would be very difficult. But with our new rules, this is pretty easy. The 8 multiplies the 1 out front to give us 8x to the 7th. The 5 multiplies the positive 12 to give us plus 60x to the 4th. The 4 multiplies the negative 4 to give us negative 16x to the 3rd. The 3 multiplies the 10 to give us plus 30x squared. The negative 6x to the 1st, 1 times negative 6 is negative 6, and this becomes x to the 0, but remember x to the 0 is just 1, so we usually don't write that. And then a constant, your derivative of a constant is 0, because if you had y equals 5, it would be a horizontal line, and the slope would always be 0. So this would be our derivative. For our next example, we want to know where will the tangent line be horizontal. This will come into play because we saw a few videos ago when we were graphing, it had a horizontal tangent line at turning points, at maxes and mins. So this we'll be able to use as a tool eventually. Well, if you have a horizontal tangent line, that means the slope of that tangent line is 0. Well, your slope of the tangent line is another way of just saying derivative. So we really want our derivative to be 0. So we'll start out, we'll take our derivative, we'll get 4x cubed minus 12x to the first, and then our constant derivative is 0, so that goes away. And we want to know, when is this derivative going to be equal to 0? Because that'll be saying the slope of our tangent line is 0. So we'll say 0 equals 4x cubed minus 12x, and now we'll just solve for x. We can pull out a 4x and be left with x squared minus 3. We'll set 4x equal to 0, and we'll get x equals 0. We'll set x squared minus 3 equal to 0, and we'll get x squared equals 3. When you take the square root, make sure you do plus and minus. So we will have horizontal tangent lines at x equals 0, x equals square root of 3, and x equals negative square root of 3. Now notice, though, the question doesn't want to know just the x values. The question wants to know the points. So we've got to find what are the y values that go with each of these. Well, 0 shouldn't be too bad. When you put 0 in for x to the 4th, it wipes out. When you put 0 and negative 6x squared, it wipes out. So we'll just have 4 left. Because they're even powers that we're plugging into, we'll get the same thing whether we plug in square root of 3 or negative square root of 3. So by plugging in square root of 3, we should be able to get both y values. They'll be the same. Well, this is really 3 to the 1/2 to the 4th. Multiply your exponents and you get 3 to the 2nd. So this just becomes 9. square root, and it's just the part inside, so that becomes negative 18. And carry down your 4. When you bring them all together, you end up getting negative 5. And the reason it's the same for both is because when we raise a negative number to an even power, so to the 4th or to the 2nd, it'll come back positive anyway. Okay, here's a picture of that. The blue is our original function. We've got our horizontal tangent lines at those points we just found, positive and negative square root of 3, comma, negative 5, and 0, comma, 4. So we have an equation to represent the motion of a particle. So S is like our position function. We're saying that's 2t cubed minus 5t squared plus 3t plus 4. S is going to be in centimeters, and t is going to be in seconds. First thing we want to do is find the acceleration. Well, we talked the other day that S of t was our position. S prime of t, our first derivative, would be our velocity. And our second derivative, S double prime of t, is our acceleration. So what this question is really saying is find the second derivative. So S prime would equal 3 times 2 gives us 6, and we'll have t squared, minus 10t. 3t, the derivative of 3t is always just 3, because the slope of that part will always be 3, and our constant has a slope of 0 always, so that goes away. And I guess we can do that, S prime of t if we want. So S double prime, just take the derivative again. We'll have 12t, and then we'll have minus 10. The constant 3, if you have y equals 3, that slope is just 0. And then in the second part, they want to know what's the acceleration after 2 seconds. Well, that's saying we want to find S double prime of 2. So we'll just plug in 2. We'll get 24 minus 10, and we'll get back 14. Now keep in mind, our position was in centimeters, our time was in seconds, and acceleration is always your distance per the time squared. So this is going to be centimeters per second squared. Often in physics, you see meters per second squared, but we had centimeters in this case. And that's all for today's video. We'll see you next class period.